In previous videos, we've seen an introductory example for the simplex method, various special cases. So now let's have a look at how the simplex method looks like in general. So here we are looking at linear programs in equational form. A is an m times n matrix, where m is the number of constraints, n the number of variables, and we call that a feasible basis, means that we have a subset of the indices such that if we take the corresponding columns in A, we get a non-singular matrix, so a matrix of full rank, and the corresponding solution, which we then call basic feasible solution, is non-negative. And an example here we have a linear program in equational form. These are the corresponding A, C, and B. Now in the simplex algorithm we use simplex tableaus, and let's describe those in general. So a simplex tableau has the following form. Given a basis, we write the basic variables, so this is a vector of basic variables in the form of p, so that's just a vector of constants, plus some function, linear function in the non-basic variables. So q is a matrix here of dimensions m times n minus m, and xn are the non-basic variables. And also the objective function is a z0 plus, and then some linear combination of the non-basic variables. So this is how a simplex tableau looks like in general. So let's take a look at this by example. So here, this is how a simplex tableau could look like. And let's check that this actually matches the description down there. So this here, the vector of x3, x4, x5, that's our xb. 1, 3, 2 is p. Then this is a q times the xn. Let me write this down here. So we have x3, x4, x5. That vector is 1, 3, 2 plus, and then this here is our q times x1, x2, x1, x2 are non-basic variables here. Also z I can write as z0, which in our case simply is 0, plus r transposed. This would be 1, 1 times x1, x2. Yeah, because here we have coefficients here are 1 and 1. Yeah, so this is how a simplex tableau looks like. Now, knowing this, it would be interesting to know that given my linear program and a selection of a basis, what are the values of p and q and z0 and r? In the previous examples, we always derived this step by step from what is given, but we can also formally describe this, obviously. So given all of those numbers here, or all of these matrices and vectors, there will be a description of the p, q, z0 and r, and this description is given in this lemma here. Lemma 5 the number refers to the number of the lemma in the book by Gärtner and Matuszek. And what it states is, yes, indeed, we can find q, p, z0 and r, and they are the following: this number, that number, that number, and so on. We make use of the fact that AB is non-singular, so we can invert it, and we get all of these expressions. And as you see, AB to the -1 shows up quite a bit. You shouldn't try to memorize this. You saw in the introductory example that it's always very easy to compute these tableaus. So you don't actually have to know these formulas. You can actually derive them from what you already know. And let's actually do that now. So let's prove this lemma. So we want to prove that all of these vectors and matrices are as stated. Recall, this is our what this should kind of add up to. Now, if you take ax equals b, then we can first rewrite the ax as abxb plus an xn, and then we can bring the a and xn onto the other side. So we have this expression ab xb is b minus an xn. Now, if we multiply these things with the inverse of ab, so ab to the minus 1, so that goes away. I keep xb, and on the other side I have this expression. Now let's have a look. What does this already show? So we wanted to have that xb is p plus this, and we wanted to show that p has this form here, and we see that here, ab to the minus 1 times b. This is exactly what we get, p, and the q times xn is ab to the minus 1 times an, so this is our q with a minus sign here. So this already proves this part of the lemma. We now just need to check that z0 and r are also what you would expect, and for that we can simply plug in the xb as we calculated it already. So z, we can write that is c transpose x. We can write it as the part with b xb and the part with xn, and plugging in xb as above, so this here, which we had here, then, and rewriting this, we get exactly this expression for z0 and this expression for r. Oh, this is r transposed, so if you transpose it, you get r. And this proves the lemma. But the important message here simply is, given the LP and the basis, we can compute all of those values. So now we have a general form for the simplex tableaus, and for that we can describe decisions in our algorithm. For instance, so here we have a simplex tableau, here written in matrix form, in particular with R transposed here. So if, for instance, R is non-positive, so here, what does that mean for our basic feasible solution? Yeah, so if in R there's no positive entry, it means there's no variable to swap in, then we already know that our solution is optimal. Yeah, so on this we can simply read off by looking at this vector here. Let's take another one. So if I have a non-basic variable, let's call it xv, it can enter the basis if its coefficient in R is positive. Yeah, so only if it shows up positively here. I mean, here this means the coefficient in R of x for x3 is 1, and therefore I can swap it in. Here it is -2 for the x5 I cannot swap in. And then if I'm doing this swap, I have to decide which variable should leave the simplex tableau, and this I always do by looking at which of the variables constrains the one that I want to swap in most, and so that we can express in terms of those numbers here. And this is simply, I look at this quotient here. This is the p as it shows up for the corresponding variable, let's say at pu. I divide this by the QUV, and the variable for which this quotient is minimal, that is the one that I'm going to swap out. And in case I'm taking the minimum over an empty set here, so there is none, which constrains the variable that I want to include in the basis, then actually we have an unbounded LP. And also there might be several choices for the variable that is leaving, and then we need appropriate rules to choose which one. This already now describes the algorithm, and we can check whether that algorithm is correct or prove that it's correct. We're not going to do that proof here, but let me at least show you the lemma that we would use in the proof, and some ideas of how to prove it. So what we need to prove is that if we have a feasible basis with a corresponding tableau, and we pick the entering and leaving variable as just described, and we get a new basis by taking u out of the basis, adding v to the basis, then we again get a feasible basis. So that is something we need to prove. Then also what we need to prove is that if we cannot find such an xu, then the LP is unbounded. And those together show that the simplex method is correct. And as I said, we're not going to do it. It's essentially a little bit of matrix calculation. Essentially what we need to show, first of all, that the corresponding matrix for B prime, so the columns of A corresponding to B prime, that again is a non-singular matrix, and then also that the corresponding solution is also feasible.